Hello guys, my name is Gibran
My name is Kimora.
And my name is Bianca.
and we're from Physics Period 1. So the problem for this project is that we need to find a way to make a roller coaster that can propel a marble until the end of the track without an external motor by using the law of conservation of energy.
Our project focus question is, how does the law of conservation of energy explain the motion of a roller coaster, and what factors in my roller coaster design affect energy transformation and efficiency? Our big question for this semester is, why do visionary leaders adapt? Our project focus question is related to the big question because both involve making adjustment to achieve the best outcome, require understanding how things works, identifying areas for improvement, and making change to make things run smoothly.
To start explaining the roller coaster project, we must first understand a few of the key concepts related to it, starting with the law of conservation of energy, which essentially states that energy is neither created nor destroyed. Instead, it transforms or converts from one form to another. Therefore, if all forms of energy were taken into account, the total energy of a particular isolated system will always remain constant. Another key concept that needs to be addressed is energy transformations, building up of the law of conservation of energy. A common day-to-day example of energy transformation is your phone, which it uses electrical energy and then changes it to stored energy within your phone, which then changes into light energy for your display, sound energy for any audio that comes out of your phone, as well as expends itself as heat energy, which you can often feel when you use your phone for too long and it gets hot.
As previously mentioned, the law of conservation of energy states that energy cannot be created or destroyed. It can only be transformed. This means that in our roller coaster, the energy from our marble is converted into new other types of energy. As we can see, we got a rough sound coming from the marble that is in contact with the roller coaster. Also a vibration when the marble is rolling down, making a turn, or doing a loop. And it creates heat because of the marble's movement on the paper roller coaster track, which causes friction.
As mechanical energy depends on an object's position as well as the object's motion, its magnitude comes from the sum or total of the moving energy and the stored energy, also known as the kinetic and the potential energy. Since the roller coaster model has a lot of curves, a lot of turns, and a lot of different heights, the mechanical energy constantly changes throughout the model, which is especially seen at certain points, such as the point of maximum potential energy, which is the initial drop of our roller coaster. It has the maximum potential energy because it is the greatest height or the highest peak of our roller coaster. On the other hand, this is the maximum kinetic energy point because it is the lowest point, which means that the marble has accelerated enough to get maximum velocity. For our measurements based on observation, the highest point of our roller coaster is 46.5 centimeters, and then point B is 21.5 centimeters, the loop peak is 16.5 centimeters, and the marble's mass is 5.5 grams. The relevant formula for the first part of our calculation is kinetic energy is half of mass times velocity squared. Potential energy is mass times gravitational acceleration times height of the position, and mechanical energy is the sum of potential and kinetic energy. The first set of calculations is 4.A, in which we find the kinetic energy is 0 joules, and the potential energy is 2.5 times 10 to the power of negative 2 joules. The next set of calculations, which is the calculations for point B, works directly according to the law of conservation of energy because it assumes that the total energy remains constant and it finds the velocity based on that. According to that, the kinetic energy at point B is 1.34 times 10 to the power of negative 2 joules, the potential energy is 1.16 times 10 to the power of negative 2 joules, and the marble's velocity is 2.21 meters per second. Building off of that idea, we find that the kinetic energy at point C is 1.61 times 10 to the power of negative 2 joules, the potential energy is 8.89 times 10 to the power of negative 3 joules, and the marble's velocity is 2.42 meters per second. For half of the height, the kinetic energy would be 1.25 times 10 to the power of negative 2 joules. The potential energy would be 1.25 times 10 to the power of negative 2 joules, with a marble's velocity at 2.13 meters per second. And for the point of a third of the height, the kinetic energy would be 1.66 times 10 to the power of negative 2 joules. The potential energy is 8.3545 times 10 to the power of negative 3 joules, and the marble's velocity would be 2.46 meters per second. So to calculate the work done by non-conservative forces, we find the difference between the mechanical energy at the start with the mechanical energy at the end, to which we find is 2.4 times 10 to the power of negative 2 joules, and we use that to find the power, which is 1.04 times 10 to the power of negative 2 watts.
Thank you for watching the video. Toodles!